It is nothing but complex representation of bandpass signals and system. Okay, so if you just recall, we have seen how to represent the bandpass signal S of t in terms of the low pass signal. Okay, so this is the bandpass signal representation, and this is the low pass signal representation. In the same way, we have also seen for the system H of t is a bandpass system here, bandpass system. Okay, so this we have represented in the low pass. Okay, low pass system representation. Okay, so now here in this topic he is asking you to represent the complex representation of bandpass signals and systems. Okay, it means that here you will have the system. It is a bandpass system. S of t is a bandpass signal which is given to the system bandpass system, which is H of t, and X of t is the output of the system. Okay, now what I need to do, I need not find the relationship between X of t, H of t and S of t, but I need to find the relationship between X tilde of t, H tilde of t and S tilde of t. Okay, we have already done all this. Anyway, we'll just revise. Okay, so in order to find the relationship between these three, let us deal with the normal representation what we have learned so far. Okay, so if this is any system, LTI system, if it is an LTI system, any system, it can be bandpass, low pass, whatever it might be, any system, if it is having some input signal, then to find the output X of t or any output, so X of t is the output here. So to find the output, we need to convolve the system function with the signal. Okay, this H of t and S of t should be convolved, or the same thing I can even write as S of t convolution with H of t. Anything is fine. Okay, because it satisfies commutative law. Okay, now let us represent the same thing in convolutional integral form. So X of t is nothing but integral minus infinity to plus infinity. H of t you have, so instead of H of t I'll take as H of tau, S of t minus tau d tau. This is a expansion of this convolution by using the convolutional integral. Okay, one second. Okay, so X of t is this. Okay, so this is what we already seen from very basic signals and systems and all that. Okay, in that subject also you have seen DSP, also you have seen in all that you have already learned until here. Okay, but here if you observe, it is giving the relationship between X of t, H of t and S of t, but I don't want the relationship between X of t, H of t and S of t, but I want the relationship between X tilde of t, H tilde of t, S tilde of t. Okay, in order to do this, what we'll do, we will represent this H of tau, S of t minus tau by using the pre-envelope. Okay, so what is pre-envelope? Pre-envelope, if you just recall, we know how to represent the pre-envelope equation. See, H of t is a bandpass system. Bandpass system. So H plus of t we will write as H of t plus JH tilde of t. Okay, this is how we represent. Okay, or if I want to find H of t is nothing but real part of H plus of t, right? This we already know. Okay, the same thing I'll just represent here. So I need to find H of t. Okay, so let H of t is equal to real part of H plus of t. Okay, but anyway, I want in terms of H of tau, I'll write here only H of tau is equal to real part of H plus of tau. Okay, let me, this I'll consider as equation A. Okay, then I'll write one more equation. In the same way, S of t is also a bandpass signal. So S of t can be represented in the same way. Like I can write as S plus of t is equal to S of t plus JH S tilde of t, where S tilde of t is the Hilbert transform, S of t is the bandpass system, bandpass signal. So if I want to find S of t is nothing but real part of S plus of t. Okay, so the same thing I'll use here. Okay, so let S of t is equal to real part of s plus of t. Okay, real part of s plus of t. But here I don't want s of t. I want s of t minus tau. So wherever I have t, I will replace with t minus tau. So I will write as re of s plus of t minus tau. Okay, so let me substitute this. This I'll consider as b, and this I'll consider as equation 1. Okay, let us substitute a and b in equation 1. So it will turn to x of t is equal to integral minus infinity to plus infinity. Whatever we have, let me write that first. So s of t minus tau d tau. Okay, so now here I'll substitute the values of h of tau and s of t minus tau. So integral minus infinity to plus infinity is h of tau is nothing but real part of h plus of tau. In place of s of t minus tau, I'll substitute the b equation re of s plus of t minus tau. Okay, we can write it in this way or here only. You know how to represent s plus of t in terms of complex envelope. It is nothing but s tilde of t e power j 2 pi fct. Okay, that also you can directly substitute. Anyway, let me write one more equation here also. H plus of t is nothing but you already know it as h tilde of t e power j 2 pi fct. Okay, so these equations you can directly substitute here, or let me go in this way only. Okay, so I can write this as real part of this real part and this real part. Okay, if they are getting multiplied, I can write it re I can take out, but the amplitude will be reduced by half. Okay, it will be this will be equal to half of re integral minus infinity to plus infinity h plus of tau s plus of t minus tau d tau. This is what you need to remember. The re the real part of this signal and the real part of this signal, if you are multiplying and then integrating, it will be equal to half of real part of this integration from h plus tau or s plus of t minus tau d tau. Okay, so this is what the new thing which you need to note it down. So just put a star there so that you will understand, or you can write it as remember, because we are not proving the properties of pre-envelope since it is not there in your syllabus. So directly I have represented it, so you can just make a note. You have to remember this. Okay, so x of t is equal to half re. Okay, fine. Let me write the equations of this first and then we'll come back here. So h, we know that h plus of t is nothing but h tilde of t e power j 2 pi fct. So that h plus of tau, t I am replacing it with tau. Okay, h plus of tau will be h tilde of tau. Wherever I have t tau or t, I have to replace it with tau. So h tau of h tilde of tau e power j 2 pi fc tau. Okay, this I'll name as equation C, and let me name this as equation 2. Okay, in the same way, we also know that for the signal s plus of t, it is nothing but s tilde of t e power j 2 pi fc tau. Okay, so in place of t, you have t minus tau. So s plus of t minus tau is nothing but s tilde of t minus tau. Wherever I have t, I need to replace with t minus tau. So it will be e power j 2 pi fc t minus tau. Or I will just simplify this. So it will become h tilde of t minus tau e power j 2 pi fct minus j 2 pi fc tau. Okay, this I'll name as equation D. Substitute C and D in 2. Equation 2 is this one. Equation 2 is this one. I need to substitute that in C and D in this. So here x of t will become, x of t will be equal to half re of integral minus infinity to plus infinity. In place of h of tau, you have h tilde of tau e power j 2 pi fc tau into, in place of s plus of t minus tau, you have equation, you can substitute equation d. So it is nothing but s tilt of t minus tau e power j 2 pi fct minus j 2 pi fc tau d tau. Integration is with respect to tau. Okay, this is a flower bracket. Okay, so this is equal to half re of, let us rearrange. This is in the form of a power m into a power n, so I can write as a power m plus n. So that let me rearrange. So integral minus infinity to plus infinity h tilt of tau s tilt of t minus tau e power j 2 pi fct. A power m into a power n can be represented as a power n plus n. So the same thing I'll use here also. 2 pi fc tau plus this one plus j 2 pi fct minus j 2 pi fc tau. Once again, let me write it again so that it will be properly visible. Plus j 2 pi fct minus j 2 pi fc tau. Okay, this one and this one will get cancelled, and I'll be left out with e power j 2 pi fct only. Okay, so let me write this. This I'll erase. So this x of t is nothing but half re of integral minus infinity to plus infinity h tilt of tau s tilt of t minus tau d tau. Now, no, once again, d tau. Anyway, if you observe, here you will be left out with e power j. Okay, let me write one more step. E power j 2 pi fct d tau. Okay, anyway, this is independent of tau. I can take it outside. So half re, or I'll write in the other way. Re of x of t is equal to re of this half also I'll take inside. So it will be half integral minus infinity to plus infinity h tilt of tau s tilt of t minus tau d tau into e power j 2 pi fct. Okay, this I'll name as equation 3. Okay, generally we know how to represent x of t in terms of complex envelope. Okay, so x of t is nothing but re of s x plus of t. This you know already. Okay, same how we have represented for this system and the signal h of t and x of t, how we have represented there. In the same way we can represent the output x of t also in this way. So which is nothing but re of x plus of t is nothing but x tilt of t e power j 2 pi fct. Okay, this I'll name as equation 4. Now we can compare equation 4 and equation 3. Okay, from this I can write as, see if you observe x of t, left hand side both are same, right hand side re. Okay, in place of x tilt of t you have half integral minus infinity to plus infinity h of tau s tilt of t minus tau d tau. Okay, let me write that. X tilt of t is nothing but half integral minus infinity to plus infinity h tilt of tau s tilt of t minus tau d tau. Okay, and this one this e power j 2 pi fct, and here also I have e power j 2 pi fct. Okay, so only thing is x tilt of t, from this comparison I've got as half integral minus infinity to plus infinity h tilt of t h tilt of tau s tilt of t minus tau, or I can even write this as 2x tilt of t is nothing but integral minus infinity to plus infinity h tilt of tau into s tilt of t minus tau d tau. Okay, so if you observe, this is nothing but the expansion of convolution, right? H tilt of t is getting convolved with s tilde of t. Okay, so just write its integral. Integral minus infinity to plus infinity h tilde of t I can write as h tilde of tau, and s tilde of t I have to write as s tilde of t minus tau d tau. Okay, right. So this entire thing I can just write as h tilde of t convolution with s tilde of t. Okay, so if you observe in the time domain, I've got the relationship between x tilde of t, h tilde of t, and s tilde of t. Okay, so whenever they ask you to write the time domain approach of the subheading is very important, complex representation of bandpass signals and system, then you need to write all this. Okay, so the same thing I can just represent in the form of a block diagram as s tilde of t. If s tilde of t is the input and h tilde of t is the system function. Okay, low pass representation, everything tilt. If tilt is there, it means it is low pass representation or complex representation. Low pass representation and complex representation both are same. So here x tilde of t. See here, I'll get as 2x tilde of t, which will be equal to s tilde of t convolution with h tilde of t. Okay, this is the overall representation. Still I have something to say, but I want to know whether this is clear to all of you or not. Is this clear to everyone?
Yes, ma'am.
Anybody?
Yes, ma'am.
Okay, fine. Okay, so see, if you don't understand, you please specify where you didn't understand. Okay, so that I'll explain you once again. Okay, fine. So now I'm able to get the relationship between x tilde of t, s tilde of t, and h tilde of t. For further analysis and representing in terms of in-phase and quadrature components, let me do some a little more mathematical analysis. Okay, so generally x tilde of t, it is a complex representation. So complex representation, I can represent it as in-phase and quadrature component as xi of t plus j xq of t, where xi of t and xq of t are the in-phase and the quadrature components of x tilde of t. Okay, and these are real valued functions. Okay, now what I'll do, I'll multiply the entire equation with 2. Multiply this I'll name as equation 5. Multiply equation 5 with 2. So when I multiply equation 5 with 2, it will become 2x tilde of t, which will be equal to 2xi of t plus jxq of t. You may ask me why you are multiplying with 2. Okay, see here in the equation I have 2x tilde of t. That is the reason I'm just doing with 2 only. Okay, 2xi of t plus 2jxq of t. Okay, this I'll name as from equation 6. Okay, so you already know the relationship between x tilde of t, s tilde of t, and h tilde of t. See how in the same way how we have represented for this x tilde of t in terms of xi of t and xq of t, we can also represent for we have already seen how to represent that. H tilde of t can be represented as in terms of in-phase and quadrature component hi of t plus j hq of t. Okay, in the same way s tilde of t in terms of in-phase and quadrature component as si of t plus j sq of t. See, all these equations we have already seen. Okay, I'm just applying it here, that's it. Okay, so let me name this as 7. Let me name this as 8. Okay, now what I'll do, we already know the relationship. See, now what I'm doing is I'm trying to build the block diagram by using this hi of t, si of t, hq of t, sq of t. S of t, h of t, using these two will be finding what is xi of t and xq of t. That is what for I have taken these equations. Okay, so we already know, that. Okay, from the previous expressions we know that 2x tilde of t is nothing but s tilde of t convolution with h tilde of t, or anyway commutation, it satisfies commutation's property, so it's h tilde of t convolution with s tilde of t. Okay, so now what I'll do, I'll substitute equations 7 and 8 in 9. Okay, so let me write this properly. X of t is nothing but, I'll just take h tilt of t convolution with s tilt of t, which is nothing but h tilt of t is nothing in terms of in phase and quadrature components are hi of t plus j hq of t convolution with to x tilt of t. Okay, hi of t plus j hq of t convolution with si of t plus j sq of t. Okay, now just multiply, cross multiply, just multiply this term with this term, so it will become hi of t convolution with si of t, just normal multiplication, plus j times of hq of t convolution with si of t plus j into hi of t convolution with sq of t. Place j into place j, it will be plus j square is nothing but minus 1, so it will be minus hq of t plus j sq of j won't be there, no, not plus, 1 second, it will be hq of t convolution with sq of t. Okay, now what I'll do, I'll separate the real part and the imaginary part. So 2x tilt of t is not 2x tilt of t 2x tilt of t is nothing but, I will separate the real part and the imaginary part, is nothing but hi of t convolution with si of t, this is the real part again, so minus hq of t convolution with sq of t. J I will take common from this term and this term, so it will be j times of, okay, I'll write it down, plus j times of hq of t convolution with si of t plus hi of t convolution with sq of t. Okay, so this I'll name as equation 9, 10th equation. Okay, now what I'll do, I'll compare this equation 2x tilt of t, and I've got something, this with this equation, which one? This sixth equation. I'll write sixth equation again. Compare equation 6 and equation 10. You may ask me why I'm comparing, because here I have 2x tilt of t, and all this I've done to represent xi of t and xq of t in terms of hi and si, hq and sq. Okay, that is the reason I'm just comparing. So the sixth equation which I have is nothing but 2x tilt of t, left hand side both in equation 6 and equation 10. Let me write that equation 10 again. Equation 6 again here. 2x tilt of t is nothing but 2xi of t plus 2j xq of t. Okay, this is what your sixth equation. Okay, so just check the sixth equation. This is a sixth equation. The same equation I've just represented here. Okay, so now compare this 10 and 6. This equation and this equation, you just compare. So left hand side 2x tilt of t, and here also 2x tilt of t. I will not write for that. Next 2xi of t. 2x of xi of t, real part 2xi of t here is equal to, here the real part is this one, so it is hi of t convolution with si of t minus hq of t convolution with sq of t. This is for 2xi of t. Okay, if I want to get 2xi of t, then I need to convolve hi of t, si of t, and hq of t and sq of t, and I need to subtract both of them. Okay, that is what it implies. Let me write this as equation 11. Okay, then again 2 xq of t. See here the second imaginary part 2xq of t is equal to, here the imaginary part is nothing but this one. So it is nothing but hq of t convolution with sa of t plus hi of t convolution with sq of t. Okay, this I'll name as equation 12. Okay, let me erase this sixth equation. I don't need it here. So I need to represent this. Okay, so to represent this, I'll use this 11th and 12th equations. Okay, I will try to fit here. So SA of t, SQ of t are there, HI of t and HQ of t are there. Okay, so what I'll do first, if I want to get 2xi of t, what I need to do, Si of t and Hi of t should be convolved. So Hi of t is the system. So system I'll put in the box. Okay, signal I'll put in the as input like this. Okay, so that I'll get here as Sa of t convolution with HI of t. Right. In the same way, I should also get HQ of t convolution with SQ of t. Okay. So what I'll do, I will take HQ of t and I'll take the signal SQ of t. Okay. So the output of this will be SQ of t convolution with HQ of t. Okay, that's what is here, right? So now what I need to do, I need to subtract these two signals. So what we'll do, I'll give it to the summer where this will be positive and this will be negative, so that the output here will be equal to 2xi of t. Okay, is this clear? Is this implementation clear? Is this implementation clear to all of you?
Yes, ma'am.
Okay. So now I've just got 2xi of t. In the same way, I need to get 2xq of t also. So if I want to get 2xq of t, 2xq of t, then sa of t. This is my sa of t. That should get. See, it is a continuation. Okay, here you have the line. Okay, so sa of t is the input, and that should be given to hq of t. HQ of t, so that my output here will be equal to SA of t convolution with HQ of t. Okay, then again HI of t should get convolved with SQ of t. Okay, this is SQ of t. SQ of t. This is my SQ of t. Okay, so SQ of t should be given to HI of t. HI of t, so that my output here will be SQ of t convolution with HI of t. Okay, now I need to add these two. So what I'll do, I'll give it to the summer. Okay, so here plus plus. Okay, both plus here. So I'll get 2xq of t. So this is the total implementation of your bandpass signals and systems, complex representation of bandpass signals and systems. Okay, so whenever they ask you the time domain approach, whatever we have done now, it is all time domain approach. Okay, time domain approach. Okay, for the time domain approach, if they ask, you need to mention everything from here to here, and they may ask you for 6 months. Okay, until here. Okay, so hope this time domain approach is clear to all of you. Is it clear to all of you? Anybody have doubts anywhere, or anybody want me to repeat anywhere, you can just ask me. Is it clear to all of you? Dipshi?
Yes, ma'am.
1 second, let me connect the charger. Until then, I'll just put this, you can just copy the representation. Okay. Sonu. Have you all noted down? Have you noted down? Have you all noted down? Are you able to hear me?
Yes, ma'am.
Have you noted down?
Noting down, ma'am.
Note it down quickly. See here, you have a line. Okay, I'm not able to draw because this is the next page. Okay, so that is the reason I could not draw the line. You can draw the line. Okay, hope you are finished. I'm going for the next in the same. Sometimes they may ask you frequency domain approach. Okay, frequency domain approach. It is very simple only. Okay, so again you have different steps to find out x tilt of. Sorry, once again, let me write here. X tilt of t. Okay, again to find x tilt of t, we may be considering the frequency domain representation of h tilt of f, s tilt of f. First you will find h tilt of f and s tilt of f. So you have the equation 2x tilt of t is nothing but h tilt of t convolution with h tilt of t. This is what we have got. Okay, so if the frequency domain representation of this is 2x tilt of f, which is equal to h tilt of f convolution in time domain is equivalent to multiplication in the frequency domain. Okay, so if you know h tilt of f and s tilt of f, you can find x tilt of f, because x tilt of f is nothing but half of h tilt of f into s tilt of f. Okay, so if you know h tilt of f and s tilt of f, just by taking inverse Fourier transform of x tilt of f, we'll get x tilt of t. We need to take inverse Fourier transform of x tilt of f, so that you'll get x tilt of t. Okay, which can be represented as integral minus infinity to plus infinity x tilt of f e power minus j, no sorry, plus j 2 pi fct. Okay, plus, no, if we are finding inverse, it will be plus. If we are finding Fourier transform, then it will be minus. So df. Using this you can find. So first of all, you should know how in the first step you need to find h tilt of f. In the second step you need to find s tilt of f. Okay, so the first step one is this is what we need to find finally. Okay, so for that you have some steps. The first step is, you know the equation of bandpass system, complex low pass representation of bandpass system. If you just recall, you have got as h tilt of f minus fc is equal to to h of f. This is what we have got from the bandpass representation of system. Okay, so here what I need to do in order to get h tilde of f, I need to shift this h of f to the origin and scale it with 2. Okay, so that I'll get h tilde of f. This is the first step. Okay, shift. Okay, 1 second, let me write it only. In the first step, we know the relationship. This one we know that h tilde of f minus fc is equal to 2h of f. Okay, see, this is not the new equation. We have already found it in the bandpass low pass representation of bandpass system. H indicates system. Okay, so that is where we have represented. Okay, so to get h tilde of f, we need to shift h of f to origin, because generally the system function will be known. For that system function you will be knowing h of f. Once h of f is known, now you need to do what you need to do. You need to shift that to origin and scale it by 2. So this is the first step, so that you'll get h tilde of f. Okay, why I need h tilde of f? Because if I want to find x tilde of f, I need to know h tilde of f. In the same way, this is the first step. Any doubts you have in the first step? Okay. Step 2. We'll go to the step 2. Step 2, what I need to find? I need to find s tilde of f. Okay, so in order to find s tilde of f, what we can do, we can write s of t in terms of canonical representation of this s of t, which is nothing but si of t cos 2 pi fct minus sq of t sin 2 pi fct. And the same thing, we can represent the complex envelope. S tilde of t is nothing but si of t plus j sq of t. Okay, if you know si of t and sq of t, you can find s tilde of t. If you know s tilde of t, si of t is the inverse component and sq of t is the quadrature component. So if you know s tilde of t, you can take its Fourier transform. S of t, its Fourier transform will be s tilde of f. So s tilde of f will be known to us in the second step. Okay, in the step 3, you have to this I've already shown you. 2x tilde of t is nothing but s tilde of t convolution with h tilde of t, which is nothing but if I want to find x tilde of f, you have to take half of convolution in time domain is equivalent to multiplication in the frequency domain, h tilde of f. Okay, so this is x tilde of f. Okay, now you know your s tilde of f, you know your h tilde of f, so that you'll get x tilde of f. So in the step 4, I need to take inverse Fourier transform of x tilde of f. Okay, so that we'll be able to get x tilde of t, so that x tilde of t can be obtained. In the final step, step 5, if you want to represent x of t, then x of t is nothing but real part of x tilde of t e power j 2 pi fct. This is the frequency domain approach. Okay, so when they give s of t signal and h of t system, then what you need to do, first you need to take h tilde of f. First you need to find h tilde of f. How will you find h tilde of f? First take the h of f of the signal. Okay, and then shift that h of f to origin and scale it by 2. Okay, that will give h tilde of f. And s tilde of f, so you know that s tilde of t is nothing but in phase and quadrature component representation. If this is known, this si of t and sq of t is known for the given signal, then you can find s tilde of f. Okay, once s tilde of f is known, you can find x tilde of f. Okay, by using half s tilde of f, h tilde of f. Okay, then multiply, scale it by 2, or scale it by 1 by 2. so that you'll get x tilde of f. Once you get x tilde of f, take inverse Fourier transform, you can get x tilde of t. Okay, then finally to represent x of t, you can represent x of t as real part of x tilde of t e power j 2 pi fct. Okay, so this is a complete frequency domain approach of bandpass signals and system. Okay, so that's all with respect to this topic. Anybody have any doubts, you can ask me, or else I'll go to the next topic. Is it clear to all of you? Anybody have any doubts? Have you all understood? Is this clear, Syed? Syed? Syed is on hold. Shreya? Shreya? Shreya Tobula? Shreya? Are you able to hear me, ma? Sanjay? Prajwal?
Ma'am?
Is it clear?
Yes, ma'am.
Purnima? Purnima Bhavna? Purnima?
Yes, ma'am.
Is it clear, ma?
Yes, ma'am.
Okay. Bhavna is answering. Purnima? Purnima, are you there? Yashas?
Ma'am.
ಅರ್ಥ ಆಯ್ತಾ?
Ma'am, ಆಯ್ತು ma'am.
Okay, fine. Anyway, see, the exams, the online exams are starting from 24th, right? So this entire thing will be there. So make sure you write the assignment also parallelly. Okay, so that you'll understand. Anyway, I've shared you the notes, so you can just like practice all the equations. Okay, very important. Okay, see, if you don't like, if you're not able to represent the equations, it will be very tough for you. Okay, so practice all from now only. Okay, fine. Anyway, I'll just go back. So this is ends this topic. So next I'll go to the next topic, line codes. Okay, line codes. Okay, so which data will be communicated in the digital communications? Which data will be processed in the digital communication system? Somebody answer no. Data in analog form or in digital form will be processed in the transmitter and in the receiver? Digital data or the binary data? Which data? I'm just asking you some question. See, in the digital communication, which data will be processed? Analog data or digital data?
Digital, ma'am.
Digital data.
Digital.
Okay, fine. So digital data. So digital data, in the sense, it will be either a 0 or a 1. Okay, so you have to represent this 0 or 1 in terms of voltage levels. Okay, so generally what we'll do, we will represent 1 with high voltage and 0 with low voltage, right? So here you have different formats to represent this data. Okay, this 0 1s only you can represent in different ways. Okay, and for that you have different formats. In the sense, those formats we'll see now. So you have different formats to represent this 190. So some of the formats which you have is, or which you have are unipolar. See, these all data formats which which are used to represent the digital data, it is said to be the line codes or line coding. Line coding implies coding those zeros and ones. Okay, and line codes in place. Whatever you're representing the zeros and ones, it is said to be the line codes. Okay, so here what we are doing, we are going to represent zeros and ones in different formats. Zeros and ones in different formats. Those formats are nothing but unipolar, NRZ, NRZ in the sense non-written to 0. Once again, let me write once. Non-written to 0. Non-written to 0. This is said to be NRZ. Okay, unipolar NRZ. Next one is unipolar RZ. RZ means written to 0. Written to 0. What are these codes? We'll see now. Okay, how to represent, what is this unipolar RZ, what is this unipolar NRZ, all that we'll see now. Okay, unipolar RZ means unipolar written to 0. Okay, and the third one is polar non-written to 0. Next, polar written to 0. These are some of the formats. Okay, fifth one, bipolar NRZ. It is also said to be alternative, very important. Okay, alternative mark inversion, or it is also said to be AMI coding. Okay, AMI coding or bipolar NRZ. Both means the same. Very, very important coding. Okay, sixth one, bipolar RZ. Bipolar RZ. And the seventh one is split phase Manchester. Split phase Manchester. These are 5 different of codes generally which are used to represent ones and zeros. Okay, so if I have ones and zeros that I have to represent in the digital form, so I'll be using this formats. Okay, so first we'll see one after the other. We'll see now. Okay, the first one is unipolar NRZ, non-written to 0. Okay, here in the unipolar NRZ, what happens is if I have some zeros and ones in my data, like how it will be, like let me consider one format 101101. Okay, 101101. Okay, so this I want to represent using unipolar NRZ. Okay, so how we'll do this is, okay, x of t will be equal to 1 or a. Okay, a is like normally we'll represent it with a, or you can even represent it with 1. Anything is fine. Okay, a from the interval 0 to TB. Okay, each bit, this is said to be bit. Okay, each bit will have a time duration of TB. Okay, so it will be equal to a from 0 to TB for symbol 1. Okay, and for symbol 0, it will be 0 over the complete interval. Okay, so for symbol 0. Symbol 1, you will have amplitude A throughout the time duration, and it will be for symbol 0, it will be 0 throughout the duration. Okay, so let me draw this. One second, ma. Okay. 1 second, let me save this. Let me take the new page. Okay, so in the line codes, the first one is unipolar NRZ. Let me write here again, unipolar NRZ. Okay, so in that x of t, I'm representing the pulse name, I'm giving it as x of t. So it will be equal to a from 0 to TB. This is for symbol 1. If the symbol is 0, the amplitude will be equal to 0 over the complete interval TB for symbol 0. Okay, so let me take one small example. 1 1 0 1 1 0 1 1 1 0. Okay, so this is a sequence which I have, and now I have to represent that using bipolar unipolar in RZ. Okay, one second, let me draw it properly. Unipolar in RZ. Okay, so let me take the data again. So divide it uniformly. The time duration is same for 0 also, for 1 also. Okay, let me divide it first. Okay. 1 1 0 1 1 0 1 1 1 0. Okay. 1 1 0 1 1 8.
Bro, that is sorry, bro. I did not saw. I was writing 3 10.
1 second, ma. Let me draw it again. Wait. This is time. This is x of t. Okay, I'll take the binary data which I have. Binary data, which is nothing but 1 1 0 1 1 0 1 1 1 0. Okay, so let me divide.
This my brother cut the call. Hey, you know my bro. Did you learn?
You have to divide it equally. Okay.
You learned.
Okay, so first one is 1 1 you need to represent with amplitude A. Okay, 1 this is from 0 to TB. Everything will be like TB, 2 TB, 3 TB, 4 TB. It's equally divided. 5 TB, 6 TB, 7 TB, 8 TB, 9 TB, next 10 TB. Okay, so it will be equally divided. So from 0 to TB, if the binary data is 1, then the amplitude will be 1. Okay, next again it is 1, so again the amplitude will be 1 only. Next it is 0, so the amplitude will be 0. Okay, so this is 0. Okay, then again it is 1, so 1 second, ma. So 1. Okay, again it's 1 1. Next 0 0. 1 0 1, again 1 1, finally it is 0. Okay, so if this is a unipolar in RZ. Okay, so the amplitude is A for amplitude is A if the binary data is 1. Okay, so here also it is 1. Next it is 0. Next it is 1. Next it is 1 0 1 1 1 and again 0. This is a unipolar NRZ representation. Okay, is this clear? Is this clear? This is only to show you the division. I have drawn it. Okay, if you are okay with, you need not even draw this. Okay. Is this clear? Is this unipolar NRZ format is clear? Is this unipolar NRZ format is clear?
Yes, ma'am.
No, it is said to be unipolar because we are representing with only one level, only the positive level. So that is the reason it is said to be unipolar. Okay, now I want you people to draw for 0, 1, 1, 0, 1, 1, 0, 0. Quickly draw it and show, draw it. Quickly draw it. Have you all finished drawing? Zero will be represented with 0 level. 1 will be represented with 1 A again 0 A. It should be of same duration. Okay. And just so 0 1 will be represented with A, again 1 will be represented with A, 0 is represented with 0 amplitude, 1 will be represented with A amplitude again 0 0. Okay, so this is nothing but A. Okay, so that's all for now. Tomorrow we'll see. Have you all finished drawing?
Yes, ma'am.
Okay,
Yes, ma'am.
Okay, ma'am. Okay, so that's all. We could just see one format. Rest all formats we'll see in the tomorrow's class. Anybody have any doubts? Anything you want to ask me? You can stay back. Otherwise, the class is done for the day. Hello. Anybody have anything to ask me? You can stay back and ask me. Purnima?
Yes. Yes, ma'am.
You were not there initially?
Oh, yeah, ma'am. Actually, my phone was for charge and I didn't check the timing. So I
Okay.
joined late.
Okay, fine. Otherwise, you understood, right?
Yeah, ma'am, I understood.
Okay, fine.
Thank you.
Okay. Others? Venu is there? Venu BL. Venu BL. Teja,
Yes, ma'am.
are you understanding, ma?
Yes, ma'am.
Okay. Anybody have any? Shreya?
Yes, ma'am.
You were not
Yes,
there
ma'am.
initially?
No, ma'am, I was there from the beginning.
When I was asking you, you didn't respond, no? So I got a doubt.
No, I was there from the beginning only. Actually, my mic does not work properly.
Okay. So is it clear now?
Yes, ma'am.
Okay. Sanjay? Sai Kiran?
Yes, ma'am.
Are you understanding? Are you practicing all the derivations, everything?
Yes, ma'am.
Okay, so make sure that you learn from now only. See now, as you people are listening to the class, so just take out your whatever notes I've shared and you can read that. Okay, so you'll definitely understand. Okay, so the only thing is you need to practice all the equations properly. Okay, and understand what are those equations. Okay, so anyway, I'm just again and again giving you the same equation so that you'll remember those equations. Okay, that's all. I'm leaving. Okay, thank you. Anybody have anything to talk? Okay, fine. Then I will leave the group. Thank you.